Thanks for the introduction. My name is Teng from University of Manitoba, Canada. I'm very pleasure to present the work HydroRing, supporting mixed reality haptics using liquid flow. The work was done during my internship at Autodesk Research Toronto, and where I was supervised by Fraser and Tovi Grossman. So with the development of VR, AR technologies and products, and wearable haptic devices are getting really popular as they can deliver compelling tactile and haptic sensations even at the level of fingertips. And most of the current haptic devices are used only with virtual objects. They are often made of bulky and rigid mechanical structures and motors that are mounted directly to the user's hands and fingers, which could easily impede the user's natural cutaneous sensations and dexterity. And in many mixed reality scenarios, users need to frequently switch between interacting with the virtual and interacting with the physical objects. And in such cases, the degree to which a user's fingertip is covered by rigid material directly affects how they could actually interact with the physical world. And of course, there are some existing approaches to fulfill such needs in the mixed reality scenarios. So for example, the size of the haptic device could be reduced with a pneumatical approach, but its form factor is still rigid. And the EMS could be used to trigger virtual force feedback while the user is holding a physical object. So this approach is promising, but it's limited to the kind of sensation that can be produced. And up to this morning, we thought we were the first to propose a feel-through haptic solution, the tactile, which was presented just a few hours ago this morning. They applied electro-tactile feedbacks with a thin film form factor attached to the skin. Well, even though we are a little bit later, we have the sensation of the temperature and the pressure to these feel-through haptics, which I will explain later. And in this work, we developed the HydroRing, a mixed reality haptic device that enables virtual haptic feedback without disturbing on the user's natural tactile sensations over the physical world while they are wearing the devices. And we used the term mixed reality haptics to describe the devices that can enable virtual haptic feedbacks without impeding the user's haptic sensation of the physical world on the same location on the body. And this device allows the natural tactile sensations of the physical objects to be felt directly, or augments the natural tactile sensations with some new feelings. So for example, with these Lego blocks, not only does the device not interfere with our sensations, but it might make the Lego feel warm, cold, or buzz, depending on their configuration. So let's see the design of the device. The prototype of the HydroRing is composed of a thin, flexible latex tube that is lightly stretched over the skin and provides the tactile sensations of the pressure, vibration, and the temperature on the fingertip where liquid flow. So liquid flow has several interesting properties that make it suitable for this application. First, liquid flow has a variety of modifiable properties such as the pressure, velocity, viscosity, and the temperature. By dynamically adjusting the properties of this liquid flow inside a tube, a range of haptic feedback sensations can be created. And second, the use of liquid to deliver haptic sensations allows the end effector to be located away from the equipment that drives the flow of the liquid. Third, liquid like water is incompressible and is able to provide a strong force but can be removed from the fingertip to allow the natural sensations to be felt. And we built a hydraulic circuit to drive and control the liquid flow and generate the sensations. We use the water in our case as it is easily accessible. And water is stored in two reservoirs. One contains hot water and the other cold. Each reservoir has a peristaltic pump which draws water from the reservoir at a controlled speed computed from the desired pressure, vibration, or temperature. And the water flows from the pumps and is combined in a drip chamber. This drip chamber not only mixes the water that is at different temperatures, but also dampens the pressure fluctuations introduced by the peristaltic pumps. And the pressure and temperature sensors attached to the tubing monitor the state of the liquid and provide input to the systems to make sure the accurate sensations are being rendered. And the water travels from the drip chamber through the PVC tubing to the finger-wound ring before they actually pass through a controllable solenoid valve that stops the flow of the water. This allows HydroRing to increase pressure or produce vibration sensations. And when the valve is open, the water flows into a terminal reservoir to be later recycled. The latex tube becomes empty when the water flow is not activated, and with the valve open, or keeps static flow at a constant pressure level with the valve closed. And with this implementation, HydroRing can be used in both passive and active modes. In passive mode, it supports natural dexterity and allows the user to sense and interact with the real world. For example, users can operate with the touch screen while wearing the device. And the users can use the device in wet or dirty conditions, or perform the activities that require manual dexterity. And in active mode, it provides the tactile sensations of pressure, vibration, and the temperature on the fingertip. I will briefly explain how they work. The pressure is produced by closing the solenoid valve and preventing the water from flowing back into the terminal reservoir. As the volume of the water increases, the pressure within the tubing does as well. The system can produce pressure range from 0.1 newtons to 2.6 newtons for now. And to render vibration, the terminal solenoid valve is opened and closed in rapid succession as the water is pumped through the system. And the system is able to render vibrations from 1 Hz to 50 Hz at the moment while running a single pump at 12 volts constantly. And temperature output is produced by controlling the speed of the two pumps that draw water from the reservoirs. A PID controller is used to control the ratio of the hot to cold water. And the system is able to deliver water in the range of 2 to 50 degrees, but we limit the output to 15 to 40 to ensure users' comfort. So let's see the evaluation. So we actually run 2 user studies to evaluate HydroRing. The objective of the first study was to determine how well users could differentiate different levels of rendered tactile sensation produced by HydroRing after a brief training section. For each sensation modality, the functional range of the stimuli that the ring could actually provide was divided into 3, 5, or 7 levels of the granularity. 12 participants completed 3 repetitions of each of the 3 granularity levels for each of the 3 modalities, resulting in a total of 135 testing trials per participant. And in each block, participants were shown a training set of the stimuli corresponding to the current granularity levels. The result demonstrates that HydroRing was able to reliably produce haptic sensations at different levels, and the participants could accurately distinguish among 3 levels of haptic stimuli on each sensation, and performed relatively well even with 5 levels. And the second study was conducted to assess the degree to which HydroRing actually impedes the various natural tactile sensations. And we used 4 common tactile sensations that could be impacted by the use of the HydroRing in this evaluation, including pressure, vibration, temperature, and texture. Pressure was produced where a small platform that was constrained to move along a single dimension. Different methods ranging in weight from 0.3 to 4.8 newtons were placed on top of the platform to produce a range of pressures. Vibration was produced with a small vibro-tactile motor that could be activated between at 80 and 250 hertz. And the texture was rendered using 5 3D printed texture samples with different densities. And lastly, temperature was rendered using a small Portier module with a heat sink to provide a stimuli between 14 to 42 degrees. And similar to the previous study, each sensation stimuli was divided into 5 granularity levels, and under each sensation, the stimuli was given to the participant at a random order, and we asked the participant which level of the stimuli they just experienced. And also 12 participants completed the within subject study under 2 conditions: a baseline where they used their bare finger to perceive the stimuli, and an augmented condition where they perceive the stimuli using their index finger while wearing the HydroRing, but it's in the passive mode. Well, the difference in accuracy while wearing the ring was significantly less than without the ring. The actual effect was quite small at only 3.7%. So from this small effect, we can conclude that while the device has some impact on the user's natural perception, but the effect is quite minimal. So let's see what HydroRing can do in our different scenarios. And the feedback of HydroRing could be used to enhance existing technology that does not have haptic output capabilities. For instance, when you're reading a children's book on a tablet, the device could respond and provide haptic feedback corresponding to the elements in the book. And we also demonstrate a mixed reality scenario where the virtual elements in the scene can not only have a visual representation, but a tactile representation as well. Additionally, because the device does not substantially impede the user's natural sensations, so they can seamlessly switch between interacting with real objects and interacting with the virtual ones. And mixed reality haptics could also be used to augment existing static objects and structures, and provide feedback to augment the real world with haptic information. For instance, if the structure of the room was known by running your fingers over a wall, the rim may increase in pressure to indicate whether frame structures were located behind the wall. And while developed in the prototype of the HydroRing, we realized that further work is actually needed to develop a prototype that is more self-contained and would allow the water to be recycled. And we anticipate the future hardware development, particularly in the area of microfluidics, that will result in hardware devices such as valves and pumps that are smaller, require less power, and can be more readily integrated into wearables. And to summarize, HydroRing is a mixed reality haptic device that enables the various sensations of pressure, temperature, and vibration. Through 2 user studies, we demonstrate that by delivering tactile sensations to the fingertip where liquid flow, the user can experience the sensations of the pressure, vibration, and temperature without dramatically impacting their fingers' normal sensations. And the mixed reality haptics offer benefits for applications that require both our ability to sense the physical world and perceive haptic augmentations. With that, I would like to thank you for your attention, and I'm happy to take any question.
Thank you very much. So we have time for 2 or 3 questions.
Hi, Sean Fulmer, Stanford University. Cool project. I'm wondering if you could talk a little bit more about the testing that you did on the basically haptic perception while wearing the device. You mentioned pressure and temperature vibration, but it seems like for a lot of different things that we might want to do with our hands, like tactile spatial acuity, as well as like contact position on your fingertip or contact spread might be very important. And unfortunately, I didn't get to try the device, but I'm wondering if you could comment on kind of the effect on that side of things.
We choose the 4 sensations to test because 3 of them are actually relevant to the sensations that the HydroRing can actually produce. And but we tested it in the passive mode so that we can observe when wearing the ring how much the people's natural sensation could be affected. And then we actually build our own devices to do that and set up a reasonable range for people to tell.
Mm-hmm. So I guess just qualitatively, like when I'm wearing it, can I feel like, localized pressure at all?
Localized pressure?
Yeah, not just like, around tell that I'm touching, but know that where I'm touching on my fingertip.
So in the studies we didn't. We didn't test that specific dimension, yeah. But I assume it is highly possible because actually we ask the user to make their natural movement to touch for example, the vibrotactile motor. And if they can perform it with a different posture, for example, then they probably will be able to perceive the location information. And the latex tube, the tube actually is pretty large, that fully covered most part of the finger pad, and so that it's highly possible for them to perceive that.
Thanks.
Thank you.
Hi, I'm Shan Yuan from National Taiwan University. It seems to me that you have to carry that bottles of water when you are using it. And I wonder, have you ever tried pneumatic actuation, like using airflow? So maybe I'm wondering that if the pneumatic and hydraulic actuation, what's the difference in terms of the haptic sensation it can emulate?
There are a lot of differences between the pneumatic approach and with the hydraulic approach. The most important two are, for example, the first, the air is actually compressible and the water is not, so that we can actually reduce the latency of the time when the sensation is produced. And second, with the water, we can easily produce the temperature sensation by. Of course, we use the hot water and the cold water, but it could be hard with the airflow.
Thank you.
Speaking of latency, what is the latency of this device?
So, depends on which sensation we were producing. It's about 1 to 2 seconds for the pressure and vibration, because we have a long tube for our current implementation. And for the temperature, it's about 5 seconds. Although this is doesn't sound good, but actually it could be improved in the future by shortening the tubing and using a stronger pump, for example.
Okay, and another aspect, I wonder when you introduce the system, you only say about how the flow flows into the device. You didn't mention about how does it flow out of the device. I guess you have to have some kind of way to stop the flow from flowing out of the device to produce pressure, right?
Yeah, so I actually mentioned we used a solenoid valve at the end of the circuit to open and close the circuit.
Also, you have two solenoids, one to produce air bubbles in there to produce...
we actually used the only one. It does both.
Oh, okay. Oh, that's interesting. Okay, thank you.
Okay, one final question.
Oliver Schneider, University of Waterloo. So if I understand this correctly, it sounds like in passive mode you get the feel through, and in active mode you might block some of the textures you're feeling because you're rendering. Yeah. So I'm wondering how much thought you've given to be able to do like an overlay. You can do vibration. How possible would it be using this technology to try and feel a texture while adjusting its temperature, for example, using hydraulics?
So that's a good question, and we actually thought about it as our future work, and we think that could be a very interesting direction by combining different sensations at the same time, because the water definitely has this property. But controlling it is very hard, to be honest. So we will treat it as the future work.
Okay, thank you very much.
Yeah, thank you.